Welcome to the Deep Dive, the place where we distill dense research stacks into high-impact, actionable knowledge for you.
Today, we are really getting into the weeds on a concept that, it truly changed everything in AI. We're talking about attention.
And it all comes back to one just incredibly audacious paper from 2017. Attention is all you need.
You know, it's a bold title, but it turned out to be true.
It really did. So our mission today is to trace that idea. We want to unpack how attention went from being like a patch for these clunky old models.
A desperate fix, really.
Right, a desperate fix to becoming the fundamental engine of the transformer architecture, which is now, it's everywhere.
Before we jump into the history, let's just define what we mean by attention. Conceptually, it's actually pretty intuitive. It's based on how we, as humans, focus.
You don't process a whole scene at once.
Exactly. You don't look at every pixel of a photo with equal importance. Your brain automatically attends to the interesting parts, the faces, the action, while the background stays a bit blurry.
Okay, so in AI terms, how does that translate into math?
In deep learning, attention is basically a learned vector of importance weights. When a model is looking at one piece of data, say a word, it uses these weights to figure out how strongly that word is connected to every other word in the sentence.
So it's learning where to focus its computational energy moment by moment.
Precisely. It's asking what's most relevant to what I'm looking at right now.
Got it. Okay, so to really appreciate why that was such a revolution, we have to go back and look at what came before. We have to understand the problem they were trying to solve. Before transformers, the gold standard for sequence tasks, like machine translation, was the sequence-to-sequence model. Seq2Seq for short.
Right, and these were almost always built with recurrent neural networks, or RNNs. You might also hear about their, let's say, slightly more capable cousins, LSTMs and GRUs.
And the architecture was always this encoder-decoder structure.
Yes, and that's where the problem was. The encoder's job was to read the entire input sentence, word by word, and then compress everything it learned into a single fixed-length vector.
The infamous context vector, or sometimes called the thought vector.
The thought vector, exactly. And think about that. It had to cram the meaning of a 50-word sentence into the same size vector as a 5-word sentence.
So just how bad was that in practice? Where did it really fall apart?
Oh, it fell apart dramatically with long sentences. You could give it a short phrase, I love you, and it would translate it fine.
Yeah.
But feed it a long, complex legal sentence.
And by the end of the sentence?
It's completely forgotten what the beginning was about. The information was just overwritten. It was the ultimate information bottleneck.
A total memory failure. So this is the exact problem that the first attention mechanism from Adano in 2015 was designed to fix.
It was the perfect solution. Instead of forcing the decoder to rely on that one single squashed vector,
it gave it a cheat sheet.
A cheat sheet is a great way to put it. It gave the decoder direct shortcuts back to all of the hidden states the encoder produced along the way.
So it could look back at the entire input sentence at every step of generating the output?
Precisely. For every single word it was about to generate, the attention mechanism calculated a brand new, custom context vector.
And that new vector was a weighted sum of all the original input words.
Yes. And the weights, the alignment scores, were the magic.
Yeah.
The model learned which input words were most relevant for producing the current output word.
And that gave us those amazing visualizations, right? The alignment matrices.
Were beautiful. You could literally see the model connecting, say, the French word to the English word, even if they were in a totally different order in the sentence. It was proof that you could solve these long-distance dependency problems.
But I have to ask, calculating that for every single input word, for every single output word, doesn't that get incredibly expensive? Computationally,
That is the perfect question. And the search for an answer to that is what led to the next wave of innovation. So once the basic idea of attention was proven, people realized, wait, we don't just need to connect an output to an input.
We can use the same trick to better understand the input sequence itself?
Exactly. And that gave us self-attention, or intra-attention.
So instead of looking across two different languages, it's looking within a single sentence.
Right. If you have the sentence, the animal didn't cross the road because it was too tired, self-attention is what helps the model figure out that it refers to animal and not to road.
It's building internal context before it does anything else.
And this whole explosion of research led to a few key categories we should probably distinguish. You had the original approach, which we now call soft or global attention. That's the one you mentioned, where it looks at all the input states. It's smooth, it's differentiable, which is great for training.
But it's a computational nightmare for very long sequences.
A total nightmare. So people experimented with hard attention.
Which is what? Just picking one specific spot to look at?
Exactly. It tries to select just one patch of the input. It's much cheaper, but there's a huge catch. The act of making a hard choice like that is non-differentiable.
Okay, hold on. Why is non-differentiable such a problem? Break that down.
Well, the main way neural nets learn is through backpropagation, which relies on calculating gradients, tiny signals that tell you how to adjust the weights to reduce error. If a function isn't differentiable, you can't get those gradients.
So you can't learn in the normal way.
You can't. You have to use really complex and, frankly, unstable methods like reinforcement learning to train it.
I see. So you trade computational cost for a massive headache in training.
It's a rough trade-off. And that led to compromises like local attention, which tried to find a middle ground. But the whole field was really just searching for a way to get global context efficiently.
And we saw attention pop up in some other really kind of weird architectures too, right? Like the neural Turing machine.
Oh, yeah, the NTM. That was an attempt to give a neural network an external memory, like a scratch pad. It used attention to decide where to read from or write to this memory matrix.
And what about pointer networks?
P-tree nets were really cool. They're for problems where the output isn't new content, but it's just a sequence of pointers back to the input. Think sorting a list of numbers or finding the shortest path on a map.
So attention just becomes a way to select an index from the input.
Exactly. All these ideas prove attention was this incredibly flexible tool. But, and this is the crucial part, they were all still built on top of those slow, sequential, recurrent networks.
We were still stuck going one word at a time.
Until we got the paper that said we didn't have to anymore.
And this is where the story completely changes. 2017, attention is all you need. The transformer. They didn't just tweak the old system, they took out the core component.
They completely removed recurrence. No more RNNs, no more LSTMs. The entire model from top to bottom was built with just self-attention.
And getting rid of that sequential processing was the masterstroke.
It was everything. Because RNNs are sequential by nature, you have to finish step 1 before you can start step 2. Attention, on the other hand, can be calculated for every word in the sequence at the exact same time.
It's massively parallel.
Massively. And that meant you could train models on way more data, way faster. This is why Google and everyone else immediately pivoted their entire hardware strategy around this idea.
So how does the transformer's attention unit actually work? It introduced this now famous abstraction of key, value, and query.
Right, the KVQ framework.
Yeah.
The best analogy is probably a library retrieval system. Think of the entire input sentence as all the books in your library.
Okay, so what's the query?
The query vector, Q, is your search term. If you're looking at the word animal, the query is basically asking what in this library is relevant to animal.
And the keys are like the card catalog.
That's perfect. The key vectors, K, are the index cards for every book. You compare your query against every single key to find the best matches. A good match gives you a high relevance score.
And the values, V, are the actual books themselves, the content.
Exactly. The scores from your QK comparison tell you how much of each value, each book, to pull off the shelf. The final output is just a weighted average of all the values based on how relevant they were.
That makes so much sense. Now, the paper uses a scaled dot product. Why the scaled part? What's that doing?
That's a subtle but really important detail. In high dimensions, the dot products can get huge, and when you feed huge numbers into the softmax function that calculates the weights, the gradients can vanish to almost zero.
Which kills the learning process.
It grinds it to a halt. So they scale everything down by dividing by the square root of the dimension. It's a simple trick that keeps the gradient stable and makes training work.
So they didn't just do this once. They did it in parallel with multi-head self-attention. Why do you need, say, 8 attention calculations running at the same time?
Because a single attention mechanism might get stuck in a rut. It might learn to calculate one kind of average relationship. Maybe it gets really good at tracking pronouns, but that's it.
So you need different perspectives, like different lenses to look through.
That's a fantastic analogy. Each head in multi-head attention is like a different lens. Each one learns its own set of query, key, and value projections.
So one head could be focusing purely on grammatical structure,
while another head, at the same time, is focusing on semantic meaning. Is this word about a place or a person? By running them all in parallel and combining the results, you get a much richer, more nuanced understanding of the input.
Okay, one last critical piece. If you throw out the RNNs, you lose the natural order of the words. How does the model know the cat sat on the mat isn't the same as the mat sat on the cat.
Right, you've lost all sequence information. They solve this with something called positional encoding.
What's that?
Before the word vectors go into the model, you add another vector to them, one that's generated by a mathematical formula of sine and cosine waves. This vector gives every word a unique signal about its position in the sequence.
So even though the words are processed in parallel, each one carries a little tag that says, I'm word number 1, I'm word number 2, and so on.
Exactly. And the final piece of the architecture is that the decoder's attention has to be masked. Because during training, when you're trying to predict the next word, you can't let the model cheat by looking ahead at the answer. The mask prevents the decoder from attending to any words that come after its current position in the target sentence.
The transformer was built for language, but the real test of a great idea is if it can break out of its original domain. And in 2020, it did, with the Vision Transformer, or VIT.
This was a huge moment. For decades, computer vision belonged to convolutional neural networks, CNNs. They were built with this hard-coded assumption about images having local structure.
And the transformer knows nothing about that. So how did they make an image look like a sentence?
They did the simplest thing you could possibly imagine. They just sliced the image into a grid of little square patches,
Yeah.
say 16 by 16 pixels each.
And each patch just becomes a word, a token.
It becomes a token. They flatten each patch into a long vector, add a positional embedding, just like with text, and then they just feed that sequence of patches directly into a standard transformer.
And the model has to learn from scratch that patch number 2 is next to patch number 1.
It has zero built-in knowledge of 2D space. It has to learn it all through the self-attention mechanism.
And this is where the scaling results are they're the big aha moment. Because on smaller data sets like ImageNet, VIT was not good.
It was terrible, actually. It fell way short of what the best CNNs could do. It just overfit. It looked like a failure. But when they trained it on gigantic data sets, we're talking hundreds of millions of images, the story completely flipped.
It didn't just match the state-of-the-art CNNs, it blew past them.
It blew past them. And often while using 4 times less compute to train, the lesson was just profound.
That while CNNs are great because they have this useful built-in bias about how images work,
A generic scalable architecture like the transformer, if you feed it enough data, can learn those patterns on its own and ultimately generalize better. It learns the intrinsic structure of the domain, whatever that domain is.
so we started this journey with the old RNNs, stuck in their sequential bottleneck, unable to remember the past.
And we trace this idea of attention all the way to a fully parallel, incredibly scalable architecture that now dominates not just language, but vision too.
It's really a shift from specialized, handcrafted models to one general-purpose learning mechanism.
It totally redefines what we think of as a domain-specific architecture. It turns out, for many domains, you don't need one.
So that brings us to the final thought for you to take away. If this one single mechanism of attention can learn the incredibly complex intrinsic rules of human language and the 2D structure of the visual world just from raw data, what happens next? What other domains that we've always thought needed their own special models, like, say, audio processing, genomics, or even chaotic financial time series, are actually just waiting to be transformed by this one powerful generic idea that proves attention really is all you need?